Okay, so for simple harmonic motion and waves exam, right? The first topic in this unit obviously was simple harmonic motion. We talked about what needs to occur for simple harmonic motion to occur, okay? And the key thing for simple harmonic motion to occur was that there had to be a restoring force, and it had to vary linearly with well, it doesn't have two L's. It looks like it doesn't. It doesn't have two L's. Linearly with displacement. All right. So that means the further from equilibrium the pendulum or the mass on a spring gets, the greater the force drawing it back towards equilibrium. All right. So that's one of those important things to understand, okay, because that could easily be tested in a multiple choice question. All right, so make sure that you understand how it works. Okay, obviously the two examples we went over, okay, were the pendulum and the mass on a spring. Okay, remember that their formulas are similar. Okay, for a mass on a spring, it's 2 pi times the square root of the two things that affect the period of a mass on a spring. What are they? Mass and the spring constant, right? So it's m divided by k. Right? Any increase in mass will increase the period. Any increase in spring constant will decrease the period. Right? For a pendulum, and we did a lab on this, so expect to have several multiple choice questions about it. Okay? 2 pi times the square root of the two things that affect the period of a pendulum. They are length and gravity. Okay, should you expect to have a problem-solving question on both of those? Yes, expect a written response problem for both the mass on the spring and a pendulum in terms of their period and how that works. Okay, so a couple of multiple choice questions and a couple of written response items on just the principles and the basics of simple harmonic motion. Right? Then we talked about Hooke's law. All right, remember that Hooke's law talks about the restoring force that is present in simple harmonic motion. Okay, in particular for a mass on a spring. Okay, the force in a spring is equal to negative k times x, which shows that restoring force does increase linearly with displacement. Right, this force Fs would get bigger linearly as x gets bigger. If I double x, F will be twice as big, and so on and so on. Okay? All right. Now, could there be problem solving to do with Hooke's law? Yes, there could. How do I tell the difference between a Hooke's law problem and a conservation of energy problem? Because they give similar information.
One's horizontal, one's vertical.
Well, they could both be vertical. They could both be horizontal. Okay, yeah, in a law of conservation of energy question, they're never going to talk about force. Okay, force is not part of a law of conservation of energy problem, so that's one way. Okay, the other way is that in a Hooke's law question, how many positions am I dealing with? Okay, in a Hooke's law question, even if the object is oscillating, it's only going to ask you about one place, one displacement, one x. Okay, it's not going to ask you to compare the object at this position and at this position. If it's a comparison, then it's EI equals EF. The energy at those two positions is equal, and I'm being asked to compare them. Okay? In a Hooke's law question, if the object is oscillating, it'll only ask you about one spot. Okay? Or it may not be oscillating at all. Right? If the object is just hanging from a roof, then it can't be a conservation of energy question because it's not moving. Right? It has to be moving for a law of conservation of energy question. All right, so make sure you're looking at that. We also said that if it's a hanging object, that the force of gravity would equal the force in the spring. Or if we're talking about an object that's oscillating horizontally, the only force providing the restoring force is the net force. Okay, it's a horizontal frictionless spring. Okay, it may give you something like acceleration. If it gives you acceleration, it's definitely not a law of conservation of energy question. Acceleration is not part of it. All right, then we have conservation of energy. Okay, so conservation of energy, okay, we have EI equals EF. Right? Now, this could be for a pendulum, but if it is, then it's basically just a complete review of Unit 2, okay, because the potential energy in a pendulum is what kind? It's gravitational, and we've already covered that. So I would bet, if I was a betting person, I'm not, but if I was, okay, I would bet on having a mass on a spring because that deals with what kind of potential energy? Mechanical. They're both mechanical. What kind of energy is stored in a spring? Elastic potential energy. Okay? So we have to remember that potential energy here is 1/2 kx squared. Okay? Kinetic energy is still 1/2 mv squared, but our potential energy is different. Okay? The other things we have to remember, okay? So this is our equilibrium position. These two dotted lines represent our maximum amplitude. Right? At the equilibrium position, okay, if we have a mass on a spring, what kind of energy does the object have there? Kinetic. Kinetic only. Because the spring is moving at its maximum speed, but it's also not at all stretched or not at all compressed. Therefore, it can exert no force. Therefore, it has no potential energy. Okay? Now, if the object is here at the point of maximum compression or its maximum amplitude, it only has what kind? Potential. Because how fast is it going there? 0. That's where it's slowed down, stopped, and now the restoring force is going to start moving it back towards equilibrium. Okay? So here it has potential energy only, and here it has potential energy only. Any other positions, it would have both. Okay? Some potential, some kinetic. Okay? The big thing though is that the energy, the mechanical energy, at any position, so even if it was here, okay, the energy at all of those positions is equal. Okay? Key to know that. All right, we've done conservation of energy before, so the only thing that's different in this unit is we use elastic potential energy instead of gravitational. Otherwise, everything else is the same as it has been before. All right, that's all there is. There's really only 3 topics in the simple harmonic motion part of this unit. Simple harmonic motion itself, Hooke's law, and conservation of energy. Okay, we expect that that's probably going to comprise 3 to 4 questions in the written response and a number of multiple choice questions. All right, then we moved on to properties of waves. Okay, so properties of waves just means like terminology, understanding what a wave is, okay, how a wave works, things a wave needs, okay, so things like that. So make sure you understand things like period, okay, frequency, amplitude, wavelength, okay, things like that. Know what they are. Okay, what is a wave? It possesses energy. It's kind of energy. It's a traveling. If I want to make a wave, what do I have to do?
Disturbance.
You have to disturb something. Exactly. A wave is a traveling disturbance. Okay? If you disturb the thing the wave travels through, then you get a wave. What's the thing the wave travels through called? Medium. Okay, so I disturb a medium, and the energy of that disturbance is carried outwards from the disturbance as a wave. Okay, the wave carries the energy. It is the energy of the disturbance and travels away. Okay, so we need to understand how waves work. Okay, we need to understand period, frequency, amplitude, and wavelength. Okay, which one of those things never changes? And frequency never changes. Period never changes either. We never talked about that, but they go hand in hand, right? Okay. We also need to understand speed of the waves. What can affect the speed of the waves? The medium. And if the speed changes, then the wavelength will change. That's how period and frequency remain the same all the time. Right, so we need to understand those properties of waves, okay, and the types of waves. Okay, so if we have transverse waves, those are the ones that go up and down. Okay, if we have longitudinal waves, those are the ones that go back and forth. Okay, so make sure you could identify those or know how they operate. Okay, things like that. Okay, so that's going to be mostly multiple choice, like basically all of it will be multiple choice. Properties of waves, kinds of waves, okay, things like that. Now, universal wave equation. So V equals F times lambda or lambda over T. Only this version of it is on your test. Okay. Am I going to have a question that's just about universal wave equation? Probably not. But is it going to be part of a bunch of questions? Yes. It's definitely going to be part of many questions. So the ways that I've tested universal wave equation are with echo questions. Okay, well, those questions about, you see 8 crests, and they're traveling this far, and things like that. I'm not going to change that up. I'm going to ask you the same kind of questions on the test that I have all along. Right, so expect to get something of that nature. The other place where universal wave equation will come in will be in interference problems, like the 2-speaker questions, and in the air column questions. The standing wave questions will also require it. So it's part of basically everything in the second half of the unit, with the exception of dot. So make sure you know how to use it. Okay, make sure that you can read the questions carefully. Right? That would be my key example to you, is read the questions carefully so that you understand what you're being asked for, or any little tricks that I might be playing on you, okay, in the wording of the questions. So make sure you read them carefully. Okay, interference. So there are a couple of questions in the multiple choice about interference, but there are some questions in the written also involving interference, okay, like the 2-speaker question. Okay, that's an interference question. Where we have, okay, the 2 speakers, okay, and we have the observer down here. Okay, and we're trying to figure out whether they hear a loud or quiet sound. What determines that? Okay, so if there's constructive or destructive interference, and what determines that? Okay. Yep, I'm thinking of a little more technical way to say that.
There's a whole number of waves, and then there's versus the half.
Right, it's the number of wavelengths that are traveled from the source to the observer. Okay, so if from this speaker there's only 1 wavelength, but from this speaker there's 1.5, do they hear a loud or quiet sound? Quiet. One's arriving as a trough, the other's arriving as a crest. Okay, they are 1/2 of a wavelength apart, okay, or different, and as a result, they're arriving to destructive interference. Okay? So things we would have to do to solve a question like that, we would probably have to solve for wavelength. Okay, so we would know, we'd be able to calculate how many waves there are. Might have to do a Pythagorean theorem calculation. Okay, but those are the kind of things we have to do for that question. Remember that for a question like that, it's going to be out of like 5 marks or so. Okay, but just writing loud or quiet is not going to get you 5 marks. You have to have the proof. Okay, if you write loud and it's loud, I'll give you 1 mark and write right beside that proof question mark. Okay, that's all you will get. Okay, I'll give you 1 mark for being a decent guesser. Not a good guesser. You have a 50-50 chance. You're going to be a decent guesser. All right, the other interference questions could be diagrammatic. Okay, that is, I show you a couple of waves that are overlapping, and I'm asking you to draw what the medium would look like. Tell me whether it's constructive or destructive interference. So if I had, okay, let's say that wave and that wave overlapping in the same medium, I would ask you to draw the resulting shape of the medium. What would it look like? It has to be really, really big. Like that. Because what kind of interference is that? Constructive. Those waves are in phase. Okay, when one is up, the other is up. When one is down, so is the other. Okay, so they're arriving in phase. Right, so expect something like that in terms of interference as well. Okay, remember interference is also kind of part of the standing waves. Okay, we get those nodes and antinodes. They're a pattern. They're an interference pattern. Okay, waves at a boundary. So this is wave behavior. All right, this is where we're talking about things like reflection, refraction, diffraction, and transmission. Okay, this is also where we might have a situation where you have some diagrams and you're being asked, is the wave traveling into a slower or faster medium based on this diagram? Okay, could be some multiple choice questions like that. Okay, I told you that the day we went over it. Okay, if I have this as a before picture, okay, and this as an after picture, okay, is that wave traveling into a more or less dense medium? More. How can you tell? Okay, I've got an inverted reflection, and the transmitted wave is not just smaller, but also shorter. And if it's shorter, it's traveling slower. Those are all things that would be important, okay, in that. So expect something like that about waves at a boundary. Okay, a lot of diagrams. Okay, know what the wave behaviors, refraction, reflection, and diffraction look like. Okay, in case I show you pictures of them, stuff like that. Okay, then we got standing waves, right? So expect a closed or an open air column type of question. Okay, and probably some questions in the multiple choice about nodes and antinodes and things like that. Okay, but certainly in the written response, expect to get either a closed or open air column problem. Okay, where you'd be, expected to calculate maybe, the frequency of sound that would be heard, or the length of the tube, or the speed of the waves, or something along those lines. Okay, remember that for a closed air column, okay, at its fundamental frequency, that waveform is present in the tube. Okay, that's why lambda equals 4L. Okay, for a closed air column. For an open air column, okay, open at both ends. Okay, that's what our fundamental frequency looks like. Okay, there's half a wavelength in the tube, so lambda equals 2 times the length of the tube. Are there any other things we need to remember about air columns? In particular, closed ones. Right, it only resonates at odd numbered frequencies. Okay, this is F1. That F2, I have this waveform in the tube. What's at the top? Destructive interference, what do we call that? A node, right? There's no resonance then because there's no waves at the top of the tube. Okay, so it would not resonate at F2 or 4 or 6. It would only resonate at the odd numbered frequencies, whereas an open air column always has, okay, an antinode at either end at all frequencies. And so important things to remember there. Okay, and remember, it is only the column of air that is resonating. Okay, if this is talking about a partially filled tube, all right, so it says, this tube is partially filled with a liquid, right? The liquid doesn't count as the air column. That's a water column. It's not going to resonate. Okay, only the air column will resonate. Okay, so be aware of that just in case that comes up. Okay, like maybe it talks about a pop bottle that's partially filled with pop still. Okay, that's going to affect it. It's not the full length of the bottle. It's only the length of the air column itself that would affect this. Okay. All right, and then last thing. Okay, that's air columns. So standing waves and air columns. Okay, remember we could get standing wave question. Okay, about waves on a spring. Still the same idea. Okay, if you had your fundamental frequency, would look like that. Okay, this would be F2, this would be F1. Okay, the number of antinodes is the number of the fundamental. Okay. All right, and then air columns we already talked about, and then we ended off with Doppler effects. Should you expect the Doppler effect problem? Guarantee it. Okay, make sure you know how to solve a Doppler effect problem. When do you use plus? When it's going away from you. Okay. You use minus when it's coming towards you. Okay, we're going to keep that in mind. And remember also that a question may require you to use this formula. When would you use that formula? Right, if it gives you the temperature of the air, you'll have to use that to calculate the speed of the sound waves. Okay? We didn't use it very much, but we did use it, and it is on the formula sheet, so just be aware and remember what it's used for. All right, questions from you guys?
Please. What was the fourth kind of waves that
Reflection, refraction, diffraction, transmission.
What is transmission?
Just when it goes through. Okay, other questions? Okay, last week I posted a review package in Google Classroom for this unit. It's quite long. I don't know why, it just is. So they would just find more stuff. Okay, the first 2 pages are fill in the blank, and I do have the fill in the blank key in that same post in the stream. So that's going to be a really good one to use in order to help you with your terminology. There are a couple that we did not go over, okay, and I'll identify those here in just a minute so you know which ones you don't have to do. But it's a good way to review your terminology. And there's some problem solving after that. There's also a couple of problems in there that you won't have to do, which I will identify here shortly for you, in case you know which ones you don't have to do there. Okay, so I'll take questions all period long. If you have them, just raise your hand or pop up to my desk and ask, and I'm happy to help. Otherwise, you've got some time to review for your test tomorrow, or maybe some final exam review. It's entirely up to you, but you've got a little bit of time for that. Now remember, for the rest of the week, okay, the plan is as follows. Okay, you've got time to review today. You've got your test tomorrow. Thursday and Friday, I'm just going to do like a really quick review of the key concepts from the whole course, and I'll take questions from you guys. Your best bet to get the most out of those 2 days is to come with questions. Okay, have a look over stuff so you know, all right, I need to ask Mr. Coderre about projectile motion. I need to ask him about Newton's second law problems that are about an elevator or whatever. Hey, figure out what it is you don't get, so you can come in and ask questions of me during that time. If you need to ask me questions during exam week, remember you need to email me before you come in. Right? I'm supervising 4 different exams, so I'm not always going to be available. So email me and say, Mr. Coderre, if I came in at 10 a.m. on January 21st, would you be available? And I'll email you back and say yes or no. If it's yes, I'll tell you where to meet me. Okay? Because it may not be in this room. If there's an exam being written in here, then obviously I can't see you. Maybe see you somewhere else. I can, but it'll take me a little while to get one set up because I actually have to do all the calculations. I can't just take it on the Okay, so give me a few minutes and I'll get a speaker question. Okay, so we have a frequency of 250 hertz. Speed of sound in that room is 340 meters per second. Okay, the speakers are 3.53 meters apart, and the observer is standing 2.04 meters in front of the first one. Right? You need to calculate whether that person hears a loud or quiet sound. Right? I'll give you a few minutes on that one. Okay, so I had a request here for a Hooke's Law question. So here you go. 2.2 kilogram mass is hung from a vertical spring. The vertical spring has a constant of 25 newtons per meter. I want to know how far the spring stretches. Okay, so it's not oscillating, it's just hanging there. Okay, that's how we know it's a Hooke's Law question. Right? And we're also only told about one position. We're actually only asked to find one position here. We're not comparing two.
Can you go back and do the room?
Oh, yes, I'll go back and do that. Yeah. Okay, so to solve the speaker question. Okay, first thing I need to know well, actually, kind of the background is, what determines whether this person hears a loud or quiet sound is the number of wavelengths traveled from each source to them. All right, so the most obvious thing to solve for first would be the wavelength, since that's what determines how many wavelengths there are. Okay, so wavelength is going to be V over F. That'll be 340 divided by 250. I get a wavelength of 1.36 meters. All right, so now I know the wavelength. The next thing I need to do is determine how many wavelengths there are between speaker A and the observer and speaker B and the observer. To do that, I need to know how far it is from speaker B to the observer. Okay, and that's going to be 4.08 meters. Right? And the reason for that is I just did Pythagorean theorem. Okay, so I went 3.53 squared plus 2.04 squared, and I got 4.08 meters. Everybody all right with that? Okay. Now, when I do now that I have that, now I need to figure out how many wavelengths, okay, there are in 2.04 meters. How do I do that? Right, divide 2.04 by the wavelength 1.36. That should give me 1.5. Okay, so I just went 2.04 divided by 1.36, and that gives me the number of wavelengths. Okay, got to do the same thing here. Number of wavelengths, okay, is going to be 4.08 divided by 1.36, and that should give me three wavelengths. Okay. All right, so there's 3 wavelengths on one, 1.5 on the other. All right, what's the difference? 1.5. There's a half a wavelength difference here, so they hear a loud or quiet sound.
Quiet.
It's quiet because there's destructive interference going on. That's all there is to those questions. Okay? There's a lot of kind of finicky work, but none of it really difficult. Okay, for the Hooke's law question. Okay, I have a 2.2 kilogram mass hung from a vertical spring. What force is pulling on the spring? Gravity. Since the object's not moving, what's the net force? 0. So that means then that the force of gravity is equal to the spring force in this question, because the object's not accelerating. Right? If I know that, then I can simply say that m times g equals negative k times x. The negative is not really a big worry here, because I only asked you how far does the spring stretch. I'm not even worried about what direction, obviously it's down. But, okay, I'm not worried about that. I'm just looking for how far it stretches. So I divide both sides by k, and I'm solving for x. So we'll have 2.2 times 9.81 divided by 25. Okay, and that'll give us our displacement. So 2.2 times 9.81, okay, divided by 25. Spring's going to stretch 0.86 meters. Okay?
You just did it wrong.
All right. Keep going on that stuff there, guys.
This is what the same way with the T equals 2 pi. And then you solve for L. You solve for T, and then you plug it in.
There's a new encode. You get the period and then you plug it into the other.
Why would you solve for period? You already have m and k.
So you can put it into this equation.
Yeah.
That's for a pendulum. That's for a pendulum.
I got the same.
Well, you got incredibly lucky. That is a 1,000,000 to 1 shot.
Yay, phenomenal.
Absolute 1,000,000 to 1 shot. It'll never work again. Yeah.
Can you do a conservation?
Okay. Okay. So we're being asked about 2 different positions in this question. Okay. One of them is at equilibrium, where all the energy is kinetic. And the other is at an intermediate point where there's some kinetic and some potential energy. So we'll start out with EI equals EF. Okay, our initial mechanical energy is at our equilibrium position, where we only have kinetic energy. Our other position involves having both. Okay, so it sets up like that. Now I'm going to expand it out further. Okay, 1/2 mvi, which happens to be the maximum speed, squared, equals 1/2 mvf squared plus 1/2 kxf squared. Okay? Now, I know the final speed, I know the maximum speed, okay? I'm looking for this, the final displacement of the object. So, right now I'm going to cancel the halves. It's in every term, so I don't need it. Okay, I'm going to get rid of it. I'm going to bring the kinetic energy final over to this side, so I'm going to have mvi squared minus mvf squared equals kxf squared. Right? Then I'm going to divide both sides by k, and then I'm going to square root. Okay, that'll leave me with my final displacement. Right, so we have a 1.5 kilogram object, and it's moving at 6.2 is its maximum, right? Yeah, 6.2 squared minus 1.5 times 4.5 squared divided by the spring constant, which was 31. So 1.5 times 6.5 squared, okay, minus 1.5 times, oh, sorry, not 6.5, 6.2. Start that again. 1.5 times 6.2 squared, okay, minus 1.5 times 4.5 squared. Okay, and then I'm going to divide that by 31, and then I'm going to take the square root of that. Okay, so the displacement of that mass, when it's moving at 4.5 meters per second, is 0.94 meters. Okay?
Wait, why is it 0.94? Was it 0.94?
Yes, 0.94.
I got 0.93.
0.938. Did you round anything off?
No, I just got 0.932 instead of 0.93. I probably missed a decimal or something.
Somewhere, I think, yeah. Okay. Keep going, guys, on your review there. I'll answer more if more come up. Okay, you got an air column question here, guys, you can try. We have an open air column resonating at its fundamental frequency of 285 hertz. Okay, in air at a temperature of 28 degrees Celsius. I want to know how long the tube is. Yeah. So, we have an open air column. As soon as it says open or closed, the thing you want to do is write down lambda equals 2L or 4L. In this case, it's 2L because it's an open air column resonating at its fundamental frequency. Okay. The other things I know that the fundamental frequency is 285 hertz. Okay. The temperature of the air is 28 degrees Celsius. How is that going to help me? I needed to find the speed of the sound. Okay, so V is going to equal 332 plus 0.6 times 28. So 332 plus 0.6 times 28. All right, we're looking at a speed of 348.8 meters per second. All right, now that I know that, can I find the wavelength? Yeah. Yes. Okay, that's the next thing I need to find. Okay, that lambda equals V over F, because I'll use lambda to get the length of the tube. Okay, so 348.8, okay, divided by the frequency, which was 285 hertz. All right, so my wavelength is 1.22 meters, and that means that the tube, okay, is going to be how many times longer than that? That's right, it won't be longer. See, I worded that in a tricky way. Okay, it's actually going to be half as long. Right, I'm going to divide that by 2 because this is the formula I'm using. Okay, I want to get L by itself, so I divide both sides by 2. Okay, so I take this, divide it by 2. And I get that the length of that tube is 0.61 meters. Actually, I think I have 3 significant figures here, so
Use temperature.
well, that's right, I use temperature, so 28. So 0.61 meters is the length of the tube. All right, and then I'll do a Doppler effect question because I had a request for that as well. Okay. Okay, so there you go. You got an ambulance moving towards an observer at 25 meters per second. The observers hear a frequency of 850 hertz. If the air temperature is 16 degrees Celsius, what is the actual frequency of the sound? Okay, so for this one, we have the speed of the source, 25 meters per second. Okay, we're going to calculate the speed of the waves by going 332 plus 0.6 times 16. Okay, so 332 plus 0.6 times 16, okay, gives us 341.6 meters per second. Okay, and we know the frequency, the perceived frequency, so that's F, 850 hertz. Right, so the formula I'm using here, okay, F equals FO, V over V minus Vs, because it is an approaching source. Okay, I'm solving for FO, so I'm just going to bring the entire bracket over, which will give me then, I'll have 850 divided by 341.6 divided by 341.6 minus 25. Okay? So 850 divided by, in brackets, 341.6 divided by 341.6 minus 25. All right, so we're looking at 7.9 times 10 to the 2 hertz for the actual frequency of the ambulance. Okay, make sure you're well prepared for tomorrow's test, guys.